Hey everyone, so now we're going to be talking about compounds, right? So we've built up the idea of energy. We talked about energy is involved with matter, and then talked about the fundamental building blocks of the matter around us, which are going to be uh, atoms and the structure of atoms, their nucleus, protons, electrons, and neutrons, and then the energy structure within those atoms as well. So now we're actually going to be talking about, well, how do these atoms now come together, interact with each other to form compounds? And we talked about compounds in our first, different classifications of matter lecture as well, right? So we're going to be talking about compounds now. And so first thing that we'll talk about is most elements except noble gases combine to form compounds. And compounds are the result of the formation of different chemical bonds, right? Chemical bonds between two or more different elements, but they can also be the same element as well, right? So you can have molecules that just have the same element in them. Very long molecules, for example, biological molecules are carbon-based because carbon likes to bond with itself, right? So they can form chemical bonds between other elements and elements of their own nature. And in the formation of a chemical bond, atoms either lose, gain, or share valence electrons. Remember we talked about the valence electrons being important because they give us the identity, right? Or not the identity, the personality of atoms, right? So this is where this comes into play now, right? The valence electrons give the atoms their personality, their reactivity, how they interact with other atoms. And they do this in a way to complete their outer shell to attain what we call a noble gas configuration. So remember when we did our abbreviated electron configurations, right? Noble gas, which are our group 8 elements, in case you forgot, right? When we did our abbreviated electron configurations, we started with the most recent noble gas, right? And that's because noble gases are the most stable configurations, right? Noble gas configurations are the most stable configurations. So when atoms bond with other atoms, they want to obtain this type of configuration. And they have a filled valence or filled outer shell. The tendency of atoms to have 8 electrons, right? So we think about it, we get our s orbital, which has 2 electrons, plus our p orbital, which has 6 electrons, right? This equals the noble gas configuration, right? So to have these 8 electrons is known as the octet rule, right? And I say a tendency, and also we should put a little asterisk and a little arrow right here that says most atoms, right? Because there's, as with most things in chemistry, there's always going to be some exceptions, but we're going to focus on things that follow this octet rule, this tendency to fill their outermost valence shell, right? And so this happens in either the sharing or the loss and gain of electrons, right? So the sharing, the gain, or loss. This is for ionic compounds. And then the gain, the sharing, this is going to be for covalent compounds. We'll talk about this more as we talk about these different compounds throughout this little lecture series here. Okay, and so how do we form ions? Well, an ion, what is an ion? It's just a charged particle, right? So it means it has an uneven number of protons to electrons, right? The number of protons stays the same, so really it just has to do with the transfer of an electron in some way, right? So this can be produced when an atom loses or gains one or more electrons. And so if we gain an electron, that's called a cation, right? And a cation, so in this case, when a cation is formed when a neutral atom loses an electron, not gaining an electron. So a cation forms when a neutral atom loses an electron. This process is called oxidation, right? So oxidation is when we lose electrons. And when we get rid of one negative charge, right, we have one extra proton in the nucleus now. We still have 11 protons here, but now we only have 10 electrons. So we have 11 protons, 10 electrons. There's an imbalance there, so we have a positive charge. And the charge is indicated by this area here, right? And if it's a positive 1, we ignore the 1. But if it was a positive 2, for example, we'd put 2 plus. You put the number first and then plus. And that indicates that it is a positive ion, and that's what we call a cation. One way you can remember that is maybe you're like me, and cats make you happy, right? And if cats make you happy, then it's a positive ion, right? So that's the formation of ion. That's when we lose an electron. An anion is formed when a neutral atom gains an electron. This process is called reduction, and it might sound counterintuitive to gain an electron being reduced, but the way we think about it is they're actually making a negatively charged ion, right? So originally we only have 17 electrons, 17 protons, or neutral. We add an electron, right? So now we have 18 electrons. We have an extra electron. That's what gives us this negative charge. The charge, again, is indicated in the upper right-hand corner. And if it's a 1, we ignore it. If we added 2 electrons, it would be 2 minus there as well. So this is called an anion. And this is called reduction. You can always remember oxidation and reduction by the acronym. It's called oil rig, right? And it means oxidation is loss, right? We lose electrons, and reduction is gain. We gain electrons, right? So that's how you can always remember these processes. Reduction, this leads to anion, and then oxidation, these lead to cations, right? And those make us happy because we like cats. Okay, and so where do we get these charges from? Well, there's different types of ions, and we'll talk about those in the next lecture series, but it has to do with the group number, right? And it has to do with the group number because for simple elements, it's the easiest way to attain the noble gas configuration, right? And so that means that if you're in group 1, right, so this is group 1 right here. These are group 1 elements. These are 2, 3, 4, 5, 6, 7, and then 8 are the noble gases. The easiest way for group 1 elements to achieve a noble gas is to lose 1 electron to become like helium. All right, so I know this periodic table here is a little small, so I'll make it bigger just for a second. Right, we see that lithium, for example, is right here. The closest noble gas is helium, so it's easiest for it to just lose 1 electron to then become like helium, right? So that's how we think of this. And that's true for all of the group 1 elements, right? All of these, the closest noble gas is just by losing an electron. So group 1 elements are always going to form a +1 charge. For group 2, they like to lose 2 electrons to become a noble gas, right? It's a little bit more work to do that because they have to lose 2 electrons, but they become positively 2 charged. Group 3 elements, these become positively 3, and really we see the only one that really obeys this is aluminum because it's a metal. Boron can be a little funny, right? So we'll only treat aluminum like this. But if you ever are confused and you're given an element and it's in group 3, you can assume that it's going to be a positively 3 charge. Now we go to nonmetals, right? The nonmetals in this case, right? They aren't going to be losing electrons, right? Because if a nonmetal in group 5, for example, wants to lose electrons, that means it has to lose 5 electrons to become like a noble gas, right? So nitrogen had to lose 5 electrons to become like, not neon in this case, it would become like helium, right? It'd have to lose 5 electrons for that. And that's just not very likely that that's going to happen, right? It's a lot of energy to put into doing that. So what they do is they gain electrons to become like the noble gas to their right, right? So that means that anything in group 5 can gain 3 electrons, so it becomes an anion, negatively charged, to become like a noble gas. Group 6, they gain 2 electrons to become like a noble gas, and group 7, these are the halogens, they gain 1 electron, right? So these are what we call the oxidation states for ions that form only a singular charge, right? So this is what we call type 1 ions, and we'll talk about type 2 ions a little bit later. And that means they only form one charge, and it's based off the group number, right? So these are the ones that you want to be able to look at the periodic table and say, okay, yes, this is the charge that I get when I'm working with this ion. If you're dealing with any of the type 2 ions, you would need more information for this type of thing. But these, group 1, 2, 3, 5, 6, 7, you should be familiar with the type of charge it forms. Does it form a cation or does it form an anion? How do you distinguish between those? Well, metals, they lose valence electrons. Non-metals, they gain valence electrons. Right? And this is all to achieve the noble gas configuration. And so these compounds, they're classified into two different categories here, and we talked about this a little bit ago. And this is always the first step whenever you're looking at a compound, right? The first thing you're going to decide, is it going to be molecular or is it going to be an ionic compound? And molecular, really what we mean by this, is it going to be a covalent compound, meaning our electrons shared? So I'm introducing this idea now. Are they shared, or are electrons going to be transferred in our ionic compounds, right? These are our ionic compounds in this type, right? And how do we distinguish between them? Well, covalent compounds are going to be between nonmetals. So these are nonmetals only. And again, I'll reiterate this later. These are nonmetals only that bond to each other. And ionic compounds are going to be metals bonding to nonmetals. All right, and this is the transfer of electrons. So these are how we classify these different compounds, right? They're either covalent compounds or they're going to be ionic compounds. And this is true. We need to identify this when we're drawing the molecules, and when we're writing the chemical formulas for the molecules, and when we're naming them, because we have different rules for all of these different compounds. And the nature of this chemical bond is very important for the physical and chemical properties of the substance, right? So for example, if we have ionic compounds, they tend to have large boiling points, for example, compared to covalent compounds, but they also tend to have high solubility, meaning it's easy to dissolve in water, right? So that means that if we have a covalent compound, or an ionic compound, and we put it in a solution of water, and we have a bunch of sodium and chlorine ions that are floating around in solution, that these can actually lead to certain properties like conductivity, right? So if we hook a circuit, plug this into the wall, right? We plug this into the wall, we put electricity through here, and we see electricity has to go through into the solution, and these two wires right here are not connected. However, because the ions are positively and negatively charged, they can move and they can transfer electrons from one side to the other, goes through the circuit, and then turns on the light bulb, right? So these types of bonds, or this type of conductivity, is only possible because we're dealing with an ionic compound. If you do the same thing and you take out all of the salt, for example, and you replaced it with sugar molecules, so let's say these are a bunch of sugar molecules in here, they don't carry charge, so electricity would go through, it goes up, it goes in here, and then the current just dies here, right? It doesn't get transferred at all. There's no transfer of electrons, so the light will never turn on. Right, so the type of chemical bond determines a lot for the chemical and physical properties of the compound itself. And so how do we make these ionic compounds? Well, what happens is two ions, or a metal and a non-metal, right? So this is our metal, this is our non-metal. They get close to each other, and the metal likes to lose electrons, the non-metal likes to gain electrons. So we transfer one electron from the valence shell of this sodium atom here, and that goes to the chlorine atom, right? And what happens when we do that is we see now the sodium atom has a full outer shell, a full valence shell, satisfies the octet rule, and now the chlorine atom also has a full valence shell. And so how do these two interact then? Well, really, this just boils down to physics at this point, because we have a ball of positive charge from the sodium atom, and we have a ball of negative charge from the chlorine ion here, right? And they just interact through electrostatic forces, right? So this is electrostatic forces. The same way that, opposite sides of a magnet attract each other, positive and negative charges attract each other. And this is what we'd say is a moderately strong bond, right? So a moderately strong bond, right? So it's not going to be as strong as covalent bonds, but it's still a relatively strong bond. And so they just interact like little charged particles is how they're interacting with each other. And this interaction is how ionic bonds are forming, right? And so these bonds are called ionic bonds, right? And it's when electron transferred from what becomes the cation to what becomes the anion. From cation to anion. Right? So that's how these ionic compounds form. And so atoms that lose electrons, atoms that gain electrons, these are nonmetals usually. These form our anions. And this is just reiterating what we've said already. And atoms that lose electrons, right? These are going to be our metals, form positive anions. They form our cations, right? And so again, we have our cat. Cat makes us happy. That's why it is a positive positive ion in this case, right? So in this case, the sodium is the cation and the chlorine is the anion, right? And they both satisfy the octet rule. Chlorine achieves an argon configuration because it has the same electron configuration now as argon, and then sodium achieves a neon configuration because it has the same electron configuration as a neon atom, right? And we notice that both of these, neon and argon, they're both noble gases, right? And so how do we represent these molecules? Well, we represent them with what we call a chemical formula, right? So a chemical formula tells us how many elements of each type are in a compound. All right, so one that you've probably been familiar with your whole life is H2O, and this means that we have 2 hydrogens, and there's no 1 here, but that means we have 1 oxygen, right? In chemistry, we're usually always ignoring the 1. And for these ionic compounds, the net charge is going to be 0, right? So what determines the number of each compound, or each element, in ionic compounds is the amount that is required for the total charge to be 0, right? So what does that mean? Well, we know sodium likes to form a positive 1 charge. Chlorine likes to form a negative 1 charge. That means that overall, to get the total charge to be 0, we only need 1 of each in this case. And the example I brought up earlier, water, right? This is not an ionic compound. This is actually going to be a covalent compound, but we'll talk about those in a later lecture, right? So we need 1 of each to actually balance the charges here, right? And so for this case, it's simple because it's a 1-to-1 ratio. So the chemical formula for this would be NaCl, right? We have 1 sodium atom and 1 chlorine atom. That forms 1 ionic molecular unit. And so when the charges between the 2 ions do not balance directly, right, subscripts are used to balance the charges, right? And that's to indicate the amount, right? And this is also indicates the amount of each element, right? And so we have magnesium. This likes to form a 2+ charge because it's a group 2 element. Chlorine likes to be -1 for each of the chlorine atoms, right? So to get the total charge to be balanced, meaning we have an equal number of positive charge and equal number of negative charge, we need two total, right? Two total chlorines to balance the magnesium 2 plus cation, right? So this becomes our simplest fundamental unit. And what would the chemical formula be for that? Well, it would be Mg, and there's no subscript there because there's one of them, Cl2, right? So this would be our chemical formula for our ionic compound here. And the other things that we need to note, right, for our chemical formula is there's no spaces between elements, right? And then the subscripts indicate the number of that element. And the last thing is that, as with most things in chemistry, we don't use a subscript 1, right? 1 is always going to be implied. All right, so if you see Mg there and there's no subscript, that means there's going to be one of those in that compound. Okay, and so we'll end there, and next time we're going to talk about naming ionic compounds, and that means naming them for a given chemical formula, and then also for a chemical formula, writing the name for that compound.